Hello. So let me share the screen. So I just got to know that this is going to be the last class on calculus. So what I need to do today is go through the things about derivative, what we didn't really discuss the other day. And first of all, so am I audible and is the screen visible?
Yeah.
Okay, great. So yeah, so today I really need to go fast a little bit, but still I want to do some really important problems. So the thing is, don't expect that these two classes are going to cover all the aspects of the analysis of calculus. In general, of 10 days or 15 days crash course or workshop cannot really cover the things you are expecting to know for ISI CMI class. So what I will basically do is, and still will spend some time on solving some problems, because what we are generally trying to do is highlight the most important aspects of it, though I don't really support that thing of important aspects and not important aspects based on a particular exam. But yeah, so this course is designed in such a manner. So let's just not waste any further time and start solving the problems. Let's try this. So f be a differentiable function, okay, such that fx plus f prime x is less than equal to 1 for all x. And it's also given that f of 0 is equal to 0. So what is the largest possible value of f?
We can consider fx equal to e to the power x gx. Sorry, gx equal to e to the power x fx.
Okay, if you do that, then gx equal to e to the power x. Now,
No, we should like define gx something like that. Should such that the derivative should be 0. So we have to modify it a bit. I am thinking.
yeah, yeah. So you are on the right track, but derivative equal to 0. So how can we
Less than equal
make a
to 0.
function less than equal to 0? Right. Exactly. Yeah.
So if we are working with this function g of x, we will eventually get that f of 1 will be less than or equal to e minus 1 by e. So, I mean, if we are able to find some function for this, for which this equality holds, we are done.
So how do you know that that is the maximum possible value?
We have this function g of x. So g dashed x is less than equal to e to the power x. So we just integrate both sides, and after some manipulation, we will get that e to the x.
No, like I'm saying, like, how do you know the answer? You did the manipulation and got the answer?
Oh no, I have till now I've just been able to show that f of 1 will be less than equal to e minus 1 by. Now I still haven't shown that this equality holds up.
And how did you show that less than equal to thing?
Just as I told you, because we are given that fx plus f dash x is less than equal to 1. So
yeah, so what is your
that,
construction?
sorry?
What is your construction? What is the gx?
Yeah, gx, just like Vito Broto said, e to the x times fx.
We can
And then
another e to the power x, like e to the power x into fx minus 1. So in that case, yes, is strict.
Now you're going the right.
Non-increase.
Yeah. So we'll consider this function. So what I'm trying to do with this problem is, this is a very standard trick. So if somebody is not aware of this, so you should get used to using such manipulations. So what we are basically doing is, see, we need to somehow use this inequality, right? And this function value. So yeah, we need to some way get this form somewhere. So that is why we construct a function like this, gx equal to e power x times fx minus 1. Why do we do that? See, now if you differentiate g, what we'll get is e power x fx, right? So first, so we'll do term by term. So e power x fx plus e power x as a chain rule, right? And then minus e power x. What will that give us? E power x taking common, fx plus f dash x. So this is what we want. And what we use is this wonderful thing we have, e power x, which remains same after we differentiate. Now what to do? Now this thing is always less than equal to 0. Right? This part. Because fx plus f dash x is less than equal to 1. E power x is always greater than equal to 0. So g prime of x is always this. Right? Now what is g0? G0 is e power 0 f of 0 minus 1. That is 1. Right? So now g0 is minus 1 and g prime of x is less than equal to 0. So what can we say about g of 1? Is less than equal to g of 0. G of 0 is minus 1. So g of 1 is also less than equal to 0. Now, if that is the case, then what do we know about f of x? So now what is g of 1? So let me just write it here. So g of 1 is nothing but e times f of 1 minus 1. So this is less than equal to minus 1. So now you just have to figure out what f of 1 is less than equal to 1 minus 1. Now, when will the inequality hold?
Fx equals e to the power x minus 1 by e to the power x.
Yeah. So how to find that? Like why that is the case? Because see, all if
we are
this
given
equality
that,
should hold.
yeah.
Yeah. Go on.
Yeah, we are given that f of 1 should be less than equal to e minus 1 by e. So, I
Yeah.
mean, we'll just have to put 1 and get e minus 1 by e. So, e to the power x minus 1 by e to the power x is, I mean, a
Satisfying.
common
Yeah.
guess.
That.
Yeah.
Yeah. That is
And then we
also
can put it in the differential equation or in
exactly. Yeah.
equation.
Yeah, but to backtrace it now, if you can't guess, then what to do? That's also very easy. So if we need equality here, we need equality here, so we need equality here. So what equality we really need? We need equality here. So the g prime x should be 0. By that way, you can also construct. Like going back towards the main thing.
If we had worked with with the previous g of x, that is g of x equals e to the power x times fx, I think the answer would still be the same. A little bit of change in manipulation would be there.
Yeah. Definitely. Yeah, that will be something like greater than equal. No, but yeah. So g prime x, we need the derivative. See, the thing is, derivative greater than equal to 1 or derivative less than equal to 1 doesn't really say how much, but positive and negative really makes a difference.
Yeah, but I mean, in that case, if g of x was e to the x times fx, we would
Yeah,
we could just we would just get an inequality which would say that e to the power
g
x
prime x is greater
times
than equal to 1.
g prime x is less than equal to
E,
e to
for,
the power x,
e to the power x,
and
right?
then we could just integrate both sides to get
Both
what we
sides,
want.
yeah. Yeah, something like that should work. Yeah. But so what we really need to take away from this particular problem is whenever we are given some differential functional kind of inequality, in most of the cases, we are going to use it like this. Okay. So let's just do another one. And this one, everyone should do by yourself. Suppose G is a function. So you are, sorry, no, suppose F is a function. Consider one who are continuous and differentiable such that f of 0 is 0 and f prime x is greater than less than equal to 2 of fx and greater than equal to 0. This is true for all x. Then find f. Like solve for it. Find f. If 1, then 1. If more than 1, then all the possibilities.
Identically 0.
Yeah.
So like, can you apply mean value theorem here? Like mod of if x minus f0 by x minus 0 is less than some if dash c which is further less than 2 into mod of fx1, then again apply that theorem on f of x1 and continue like that.
Sorry, can you repeat?
Uh,
I
yeah,
got
I'm
it.
telling that let's like we apply main value theorem on fx, so then mod of fx minus f naught
Fx on
but
which interval
in
or
the
where?
0 to 1 0 to 1.
So f1 minus f0 by 1.
uh, we are selecting some x that belongs to 0 to 1, like fx minus
Okay.
f0 by x minus 1.
Yeah. So
Yeah, that thing
is
is
equal
equal to
to
some f dash c, that is further less equal to 2 into f dash to 2 into fc. Now again
yeah.
we can apply main value theorem on fc, so we can get like 2 into like um,
Uh,
c1 into c2 into c3 up to infinity, like
hmm. So what you are saying is f of x1 is equal to 2 of 2x1 times f of x2 for
yeah.
x2 in 0 to x1. Right? This should be true for all x.
Yeah.
So now you want to go on. So what you will get is something like this: 2 power n, let's say, x1 power n, I guess. Yeah. Yeah, something like that.
Yeah. Yeah. Yeah.
And f of xn plus 1. Yeah, so from this, where you are going?
Like the function is continuous on 0 to 1, so it is bounded by m. So that is equal to 2 to the power n x1 to the power n into m.
Yeah, I see, I see, I see, I
Uh,
see. So, but yeah, but what is bounded by to the power n? 1 way to the power n? What I was thinking is you can take x1 something in between 0 to half. Then this thing will go to 0, right?
yeah.
And this is bounded, so the whole thing will go to 0. So
Yeah.
what you were concluding is that the function between 0 to half is identically 0. But now what about after half? When you start with x1 to be greater than half, then this thing is not going to 0, right?
Yes.
We can consider e to the power minus 2x into fx.
Yeah, that is the solution I have, but yeah. Yeah, but this is also a nice try. You can think like how to do that and compute better. Yeah, definitely. Yeah, you can think in this lens. See, there is no particular way of solving a problem. What happens is because we all have all that constraints of 3 hours exam and okay, whatever short solution we need to have or clear input solution. So we always pick the easiest or the most comfortable way. But there might be some bigger ways which might not be very much economical, but may still be more insightful. Okay, so because this e power x thing is nothing more than a technique to solve problems. It doesn't really have any insight towards the function. Okay, I am giving a function satisfies this. Now, what do you know about the function? Just not what do you know about the function. Like, what are the deeper insights of the function? How does it behave? Finally, we're reaching to the same thing that is constantly 0. But while solving in the e power x thing, you will just get the final information that okay, this is identically something like that. Okay, but let's solve it in the way we want to solve it here. That is what you said, gx equal to e power minus s. Yeah, exactly. Yeah, so now we have to check what happens.
Should we take
We'll
minus
take e to the
2x?
power minus 2x.
Minus 2x, yeah. So just differentiate it, and then you will see that the derivative is less than equal to 0, and then f0 is equal to 0, so g0 will be something, and you can solve it. Okay. Do I really need to solve it? Just differentiate g, then check the value of g0. Then from g, you do something to f, and then find the f is constant. That's it. Okay. So let's solve another one, because so let's do this. Suppose f is a differentiable function satisfying f of 2x 2 times x. And no, it's not really given to be differentiable. It's given that it's differentiable at x equal to 0. Then prove that f must be linear. So this is a classic example of what do you say? Of telling something global about the function from a local property. So you don't know anything about the derivative of the function or whatever it is in the terms of linearity. So tell me this, what do we mean by a function to be linear? It is necessarily a derivative property, right? It's necessarily a slope property. It's a kind of differential classification of the function, if you want to put it that. So it's telling something about the global picture of the derivatives of the function. But what we know is really this and something else. So how do we go about it? Like from a local point, we are telling something general about the other points too, the derivatives at the other points.
So like, when we try like this, like we write f of x naught is equal to 2 into f of x naught by 2, and we go up to
Yeah.
to d. So limit n tends to infinity, f of x naught by 2 to the power n by 2 to the power n. Yeah.
Yeah. So what are you saying?
First we write f of x naught is equal to 2 into f of x naught by 2, and then we continue till infinity, like limit n tends to infinity, f of x to the x naught by 2 to the power n by 1 by 2 to
Yeah.
the power n, that will be, and then we can apply El Hospital's rule. Then we can find that, like we'll get
Yeah. So
f
first,
dash x naught by,
just hold on a second.
yeah,
We are getting this, right?
f of x, right, right.
So is this clear to everybody? How we are getting this? If not, stop me now. Okay. Okay. So now continue. Whoever will say.
Yeah, then we can and then apply L'Hopital's rule. Then we will get that f dash of
L'Hopital's rule where?
we can like frame it like f of x by 2 to the power n by 1 by 2 to the power n. So like
If
f0 is this is 0, we can get f0 is 0, we can get. So so we can apply L'Hopital's rule. We will get that f dash of x by 2 to the power n into x minus of 2 to the power minus n log 2, and
wait. I am not really clear here. L'Hopital rule, you were differentiating this with respect to what?
But that's
n.
not differentiable. That's a sequence. That's a discrete variable.
You were differentiating with respect to n.
Yeah.
See, all this you can't do. How do you define derivative in a discrete point? To define derivative, what you really need to have is a point should be an interior point of the set. By that, what I mean is there should be a neighborhood around the point which is inside that, in whatever set we are kind of defining our derivative. Okay. And even if you differentiate with respect to n, that is very much wrong. Even if you do that, so why are you trying to do that? So where is the x going? But this is really a nice observation that when n goes to infinity, both the things goes to 0. Like if you consider this as a sequence of n and also this as a sequence of n, both the limits are 0. That's
How the limit goes to 0?
see, this is clear, right? This part, and this is why I continue. Consider the sequence an defined as x by 2 power n. Now f of an limit n tends to infinity is f limit n tends to infinity n
That's
because of
0.
continuity at 0. Huh?
Yeah, that is 0.
Yeah.
And
Oh,
the
f of 0 is not 0. Is that? But f of 0 is 0, right? Just put 0 x.
0 is 0. Yeah.
Yeah.
But the
Then
denominator
it's,
goes to 0. How can we say that the total thing goes to 0?
sorry, what denominator?
That the 1 by 2 to the power n, that sequence also goes to 0.
Yeah.
And the denominator
Now,
comes from 0 by 0. How can we say that the total thing goes to
no,
0?
I am not saying the whole thing goes to 0.
Oh, then it's okay.
I am saying just this and this goes to 0. So That's a good observation to
Okay.
like think that we can apply L'Hopital here. Yeah. This of course might not go to 0 and will not go to 0. This is linear, right? So fx won't be 0 for all x. So here comes the most, like you just have to use it,
There's an
the
observation.
definition of, sorry?
I got an observation
Yeah, sure. Go ahead.
that in the interval 0, x and x, 2x, for all x in these two intervals, we have equal values of f dash for at least 2 points. That's why we observe that f of 2x minus f of x equal to f of x minus f of 0. And
Right.
we divide it by x and use MVT.
Definitely. Yeah. Definitely.
Can we directly use MVT unless we know that f is differentiable at other points? We are just given that it's differentiable at 0.
Can we? That is the question.
Oh, only at 0. Okay, then my argument is not okay. Sorry.
Can we use NVT? Can we use L'Hopital? These are the questions we need to ask. Very primary things. First, think about this, okay? About this small statement. F is differentiable at x equal to 0, right? Then can you say this, that f of x, or I don't know. Yeah, so kind of like that. I will not use x here. So f of y is equal to f dash 0 times y. Can we say this? Of course not, right? We can't say this if it's just differentiable at a point. So just go back to the basics, okay? At a point, its derivative is f dash 0. So at 0, the derivative is f dash 0. So what does that really mean? It means that there is kind of a linear approximation here of the function. This is the function. Around this neighborhood, we can linearly approximate the function using the line of slope f dash 0. So what is the line passing through 0 with the slope f dash 0? That is y equal to f dash 0x. That's the line. But this approximation is not exact. Of course, it's not exact. It's not supposed to be exact. It's supposed to be local around that point. That's the idea of the derivative. We define this thing called derivative just to have linear approximations locally of a function, of a differentiable function. That's all about it. When you go to multivariable calculus and whatnot, that is all about derivatives. we want to linearly approximate a curve. So there is some kind of error here. So what's the error? The error is, say, a epsilon function of y x y, and this error goes to 0 as y goes to 0, because this is approximation around the point 0. So what does this really say? It says that around 0, this is very small. So the function is really as same as this. And when y is far from 0, then the approximation fails bad.
Are you trying to approach the problem like using the Taylor expansion of f at 0, like around 0?
Forget about the problem for now. We don't really need Taylor expansion. It's sort of a, what I'm trying to say is sort of a Taylor expansion or approximation, whatever it is. So what I'm trying to say is going towards that, but we don't really need that for the problem. So first you have to understand why this is true. From the differentiation, the definition of derivative, why, from where is this coming? Okay. So that is something you need to understand. This is not if y, this is in this thing, this is f of y minus f of 0. Now f of 0 is 0. So I'm writing f of y, just f of y. So what is basically happening? Think from the definition of a derivative. What is the definition of it? So this is this idea clear? Can anyone confirm me? Like what I'm trying to say, this linear approximation thing, this epsilon y function and all that. Then we'll see mathematically from where this epsilon y function is coming.
No, sir. Could you explain it again? I missed.
Yeah, sure.
Sure.
That's what I was afraid. Okay, so the thing what I'm trying to say is, this is the function f. This is the function f. Now suppose here is the point 0. Like, forgive my drawing. Suppose this is the point 0. And I don't want to draw the x-axis. So this is the 0. So here we want to approximate the function. To approximate like this. So this approximation is not perfect. Of course, it's not perfect. But it's close enough around 0. And what is this approximated line? This is something we get from the derivative around 0, right? At derivative at 0. So this line is basically f dash 0. This is basically the approximation. Now, this approximation is quite good in the small neighborhood around 0, as you can see. But it fails when it's far from 0. So that's what I'm saying, that f of y is equal to f dash 0 times y. Okay. If f of 0 is equal to 0. And then we have an additional error in it. And that is some error function on that point. So the error differs from point to point. Times y. Because it becomes large when, so that you will see, like why this y factor is that you can't explain mathematically, but this error function should be kind of small enough around 0. So this goes to 0 as y is going to 0. That near y, when you are approximating with this linear approximation, that fits the model. So okay, so let's dive into the definition and see from where is it really coming. So fx minus f0 by x minus 0. This is the limit of this x tending to 0 is f dash. This is the thing, right? So now f of 0 is 0, x minus 0 is 0. So limit of x tends to 0, fx by x is really f dash. Right? Okay. So this is what is f dash. Now what we really want is, we want to replace f of y as f prime of 0 times y. This is what we really want to do. Okay. So what happens, and then there is some error in it. This might not be. So we define. So what we really do is, let's do it this way. So we define epsilon y to be like something like this. F of y. So that's what we define. This is the thing, right? So we define f of y by y minus f. This is the definition of epsilon. This is the way we define the error function. Now, what happens to this function when y goes to 0? What happens to this? This is a constant term, so this goes out. So what remains is this. What is this? This is again epsilon. So this is the accurate error function. The error function is supposed to give you 0 error because you are approximating at the point 0. So this is what we are saying in the last page. This is a proof of it. So what's that? Again, f of x is equal to f dash 0 times x plus epsilon of x, which is a function of x, times x, such that limit x tends to 0, epsilon of x is equal to 0. This is the meaning. And from where are we getting this? We're getting this from f dash of 0. So this is this. This is the linear approximation interpretation of derivative. So very well. So this is all I have to say. Now again, go back to the problem I'm trying. sorry. What have we? F dash 0 might not be 0. Like f dash 0 is a derivative at 0. That if dash 0 is a derivative at 0, then this is the linear approximation is the line y equal to f dash 0 x. And the function minus that approximation is this error thing.
Okay, I have an approach, but I'm actually doubtful about it. Should I tell you?
Yeah, sure.
Okay, so fix any real number c. So from the previous page, we know that f of c is 2 to the power n times f of c by 2 to the power n.
Yeah.
And we can rearrange that and write it as f of c by 2 to the power n over c by 2 to the power n, and this whole thing times c. So, and then we can take the limit as n tends to infinity on both sides. So the equation that we originally have is f of c is equal to c times f of c by 2 to the power n over c by 2 to the power n. And then we take the limit as n tends to infinity. The left hand side stays fc, and the right hand side becomes c times f dash 0, because we know that f is differentiable at 0, and our function is eventually fx equals f dash 0 times x.
So now you're taking the limit. So the limit will give you what? The limit will give you.
The limit will just give me c times f dash 0.
So that is what we did. Yeah, so that is basically the same thing. Yeah. So here you can easily manipulate it to get something as of
so is this approach like correct?
Yeah, absolutely. This is what I was also going to do, but I wanted to like set this general notion of linear approximations, because so this might not always directly fall into such formations.
Yes, I actually got the idea from the form you wrote, like at the linear approximation at x equal to 0, like at the origin.
Exactly.
It would be like y equals f dash 0 times x. That was
yeah, exactly. So what the thing is happening? The thing is happening that around 0 we know stuff, because we know that the function is differentiable around 0. The function is like this around 0. If we know the derivative around 0, then we know stuff, right? We know that this is quite a good approximation at around 0. Around 0 we know, but we don't know anywhere else. But now this comes to the rescue, because again you see fx can be given by pretty small numbers. When n is becoming large, then and this is true for all n, right? So when n is large, then this number is quite small. So this is in the very small neighborhood of 0. So again, you can say something about this. So in this case, you can actually say for large enough x, even if the x is far away from 0, you can actually tell about fx, because you can get fx from small values around 0. So you get my point. That's the whole idea of the problem. We know something local, and again we know some equation from where we can get the global values from the local values. That's the whole idea. So so we will do it the way he said. That's basically the same. So just take a look. What we do is f of c is 2 power n times f of c by 2 power, right? For any c. Now we write it as this 2 power n f of c times f of c by 2 power n by c by 2. Write it like this, right? Now we take the limit at both sides. Sorry, or not on both sides. There's nothing n here. But this is true for any n. This thing is true for any n. So if we take n large enough, then this thing is close enough to f dash 0. Right? So that's what we do. We take the limit n tends to infinity, which gives us f dash of 0. So really, but you see, there is a problem here. We actually need to work with that error function. Do you see where the problem is? See, we can't really take limit like this. We can say it's close enough to f dash 0 times c. And then we have to again use some arguments to say, okay, so this is so close, like for any epsilon, we'll get this to be less than epsilon for some large enough n. So we can tell this. But so when you're writing an exam, you can't just really put limit like this. It's
Why
true
can't
for
we
any
take the
n.
limit? Why can't we take the limit like this? I mean, what you just said, that was just the definition of a limit converging to something, I guess.
Yeah.
I mean,
but I'm
we are
saying
given
this.
that f is differentiable at x equal to 0. So for any sequence that just goes to
No,
0,
that is
this
fine.
should
Okay,
be
so yeah, so no, I am not saying so. Just let me remove a few things. Yeah, so there is no problem with this. There is absolutely no problem with this. This is fine. But from this, f of c equal to c times this. From this, how you go to the step that this is equal to c times limit n tends to infinity of the same thing.
And that is just
How?
taking the constant out of the limit. That's, I mean, it's just a standard thing that we do.
Taking the constant out of the limit?
Yeah, we have fixed the real number c. So that is just a constant now. So we are just taking limit n tends to infinity on both sides. The left hand side is a constant. The right hand side is a constant times that f of c by 2 to the power n by c to the power c by 2 to the power n.
Mm-hmm.
So, I mean, I don't think there is a problem here.
Yeah. True. Yeah, this is true for all. Yeah, definitely. Yeah, no problem. So yeah, so now we are taking limit of this, and now as this is true, so the limit will be f dash c. So it is actually in this case, the approximation is actually perfect. The approximation from 0, what we make the linear approximation, that is actually perfect. And thus the function is linear. Okay. So that's it. That is the solution, and the solution is pretty easy, as you said. But yeah, so this kind of ideas you need to remember while solving problems. It's not just looking around for different techniques. You need to really understand what the problem is demanding and what do you really have to satisfy that demand. This problem can also be stated in a continuous way. In this form, try it afterwards. Sorry. This form, that the equation is some form of this. If this is the case, then also the function is linear. Anyway, so moving forward, yeah, so what is mean value theorem? Anyone? What is Rolle's theorem? Just unmute yourself and speak.
Suppose we have a function f
Yeah.
which is differentiable on open a comma b and continuous on closed
And the
a
function
comma
is
b.
from where to where?
And the function is from say a comma b to r.
Close A comma B to R, right?
Yes. And it is differentiable on open a comma b and continuous on closed a comma b.
Okay.
Then if we have fa equals to fb,
Yeah.
then there exists a point c in the interval
In which interval?
open a comma b
Open A comma B.
such that
Such
f
that?
dash c equals 0.
Yeah, exactly this. And now what is Lagrange's mean value theorem? Again, anyone?
For any continuous function from closed interval AB to R, and it is differentiable on open interval AB,
Yeah,
then
it's the
there
same. It's the
exists
same
a
continuous function.
point, real number, yes, on the open interval A comma B such that FB minus FA
Yeah,
equal to B minus A into F dash C.
exactly. It's very good. So this is the thing. Now, do you know how to prove LMVD from rules? Or how to prove roles? Sorry, I don't know if
Yeah.
I can't hear you properly. Somebody was saying something. Hello?
Which one to prove?
Yeah, anyone. Which one you can prove?
We can prove Rolle's theorem using extreme value theorem, that a function achieves its maxima and minima on the closed and
Yes, so
bounded.
can't you prove Rolle's theorem using LMVD?
Yeah, you can when f equal to fp.
Of course. Then how do you prove LMVD?
Actually, first we prove Rolle, then we prove LMVT from Rolle.
Exactly. Yeah.
Like the function joining a comma f and b comma fp,
Exactly.
we consider the line and we use Rolle on that.
Yeah.
It's like we have f equal to fb, here we not have equal, so we make the line joining f and fb with the x-axis.
Yeah. Like we just rotate the axis. Of course. So yeah, so he said exactly the thing what we do. So this is I just wanted it to clear the fact that roles can't be proved using LMVD. It definitely can, but we shouldn't, because it's kind of a loop. People say that okay, so Rolle's theorem is nothing to worry about. It's just a special case of Lagrange's mean value theorem, but you can't prove A using B and then B using A. So if A implies B and again B implies A, you can't say that both are true. That's a circular loop you were following. So when you were told to prove LMVT, you were using, okay, so I assume Rolle's and then I'm proving LMVT. And now how do you prove Rolle's? It's nothing. It's just a special case of LMVT. So I have heard many saying like that. But the difficult part is proving the Rolle's here. Not difficult. It's pretty easy, but like that's the fundamental part. And from Rolle's theorem, LMVT is, you can prove it by constructing a function and then what is it geometrically also can think like that. And there is another thing called CMVT, that is a Cauchy mean value theorem. What does that say? That says, again, continuous function differentiable on the open interval. If there are two functions like that, f and g, and suppose what? Suppose g of b is not equal to g of a, and g prime of c is not equal to 0 for any c in A, then what we can say is f of b minus f of a by g of b minus g of a uh, g of b minus g of a is equal to f prime of c by g of c for some c. And how do we prove this?
We can construct again a function and use load
Can't we prove it from LMVT directly?
directly.
Yeah, let the other people say for I just want to hear this. Okay, so LMVT says this. Now if f is also a function like continuous and differentiable and open, then we have this, then g is also a function, so we'll have another such equation. And then if you divide the two equations, b minus a will cancel out and give us this, right? Am I doing anything wrong?
No, it is wrong.
Okay, let's
C cannot be cannot be same on both f and g. Like that, what you get as
exactly.
f dash c, that c should not be same.
Like should not be same, it's not that, but we don't get the same c from here. There might be two different c's.
Yeah.
But now it's a little bit more stronger. We are saying that there exists a c for which this happens. Like there exists one c for which this happens. So again, this is also one-liner proof. You can construct a function and then again apply rules. So okay, so these are the three, basically the three most important mean value theorems. Okay, so now tell me one thing. Okay, prove this. Okay, this is a very fundamental result, and I'm giving this as a problem. That suppose f is a function from AB to AB, which is continuous, and which is differentiable on the open interval AB, satisfying that f prime of x is not equal to 1 for all x. Then prove that f has an unique fixed point. What does this notation mean? This means there exists, and this
Does
means
not exist.
no, this means there exists unique. There exists an unique whatever blah blah blah. Like there is a unique existence of such a fixed point. There is only one fixed point, exactly. And this means it doesn't exist. So this is not expected of you to know, but yeah, so I'm just using the notations. Be familiar with, I don't know, language of mathematics or something.
By continuity, we can say there is at least one fixed point. And if there are more than one fixed points, say a and b, then consider the function fx minus x. So it has at least two roots. So by Rolle's theorem, the derivative should be at the points here. So if there should be one at some point, that is a contradiction.
Exactly. So you basically apply the roles on the g function. So first you apply IVT on g, and then you apply roles on g, where g is fx minus x. So consider gx to be fx minus x, and then we did in the last class, right, that g must have a fixed point because g of 0 times g of 1 is less than or equal to 0. That both are of different signs. And then what you do is, suppose there are two fixed points. So if there are a and b both fixed points, and g of a is equal to 0, g of b is also equal to 0. Fixed point of f, I mean. If f of a is equal to a and f of b is equal to b, then g of a is equal to 0 and g of b is equal to 0. There is some g of c, which is g prime of c, which is 0. So in that case, f prime of c is equal to what? Is equal to 1, which is not possible. Now we want to do another thing, which is kind of another mean value theorem. Okay? Like it's not a mean value theorem. That is also a fundamental thing. Suppose again, if it's such a function from a b to r, which is continuous and differentiable on the open interval a. Okay, so first of all, why don't we just say differentiable on the closed interval a? What's the problem? We have read this statement so many times in so many books. Don't you think it would be easier to say it's both continuous and differentiable over the interval closed interval a?
Yeah, but that would be more information than is required. This is the minimum information with which we can work.
Okay.
I mean,
Consider role. If it is the derivative can be 0 at endpoints, so the extrema should be attained at the endpoints.
I don't understand what you're saying. So firstly, how do you define derivatives at endpoint?
At A we define as the right hand derivative, and at B at left hand derivative.
We don't know if the function exists beyond to the left hand side of A and to the right hand side of B. To define at the point derivative at the point A or B, we have to know that the function at least exists to the left hand side of A and to the right hand side of B.
Yeah, so actually there is a very subtle point here. Okay, so just let me state this. Suppose, so just let me do it this way. Suppose there is a function from natural numbers to the real numbers. Okay? So now, can we say something like derivative at 2? Or
No.
what is it like? Why can't we, or why can we? See, a derivative is
Domain
supposed
is
to be
discrete.
something like,
The domain is discrete here.
See, what do you mean by discrete? All the things are very intuitive, right? Like,
That it
what is
can
You have to
discrete?
take a point immediately to the left of 2, and that point does not exist in the set of natural numbers. So we don't know whether that functional value exists or not.
Yeah, all of you are correct. Like, I'm not saying mathematically correct. What you're trying to say makes sense. But, like immediate left, there is no point immediately left. Like, what do you mean by
We have
immediately
to
left?
come from the left hand side continuously, but from the set of natural number we can't come continuously to the number 2, or from the right also we can't come
Yeah, so
continuously
basically
to an
what we need is a
interval.
sequence of numbers converging to 2. So this is basically the thing, the definition of derivative as it should. So derivative at x is defined something like this: f dash of x for any set x and any point x. If the limit exists, then we say that the derivative is equal to this. And what is the limit? Xn converges to x, f of xn minus f of x by xn minus 2. x and minus x. So now suppose x is a point where there is no sequence of xn converging to x. There is no sequence at all which converges to x. So then what is the value of the limit? Do you understand where the thing is going? What is the problem? Forget about that a plus h minus a, f of a, h goes to 0 and all. That is just for R. That is just for an interior point in an interval of real numbers. That is a very specific domain to work. This is the general definition. Now, if we don't even have a sequence of numbers converging to x, then how do we really define the limit of it? So if for all the sequence, the thing is going to the same point, then we say the limit exists, right? This can be any sequence xn converging to x. That is the whole concept of left-hand derivative and right-hand derivative. You take a sequence from here and then you take a sequence from here. And if you check if the limits are same from both the sides, coming from here, coming from there. But what if you can't approach that number from anywhere? Then it's not defined, right? Then we can't say that the limit doesn't exist because it is kind of vacuously true. You know what I mean? Like suppose there is no dinosaur in the world, then this statement that all the dinosaurs are very dangerous, that's true whether dinosaurs are actually dangerous or not. Or if you say something absurd like this, that the dinosaurs can, what do you say? It's something very absurd, like everything about dinosaurs is true. Because there is no dinosaur. What I'm trying to say is logically this, that false implies true. Okay? False implies everything. This is the thing, like this is the vacuously true concept of mathematics. So like another example, if I don't have any American student, then I can say all the American students I have will someday be field students. This is a true statement because I don't really have any American student. So like that, if you don't have any sequence xn converging to x, talking about limit doesn't make sense. We can't really say that derivative doesn't exist, but we also can't give any value to the derivative, any particular value. So similar to this case where there is no sequence converging to x, we will also rather get rid of all those cases where there is only a sequence from a particular direction and not from the other side. So suppose in this case, in A, at the point A, you can have a sequence converging from here. But then you don't know anything about the other side. So that's why what we do is, as I said before also today in class, that we define derivatives at points for which there is a complete neighborhood around it inside that set on which set we are working. So basically we are working now on the closed interval A. So we will only define derivatives at points where the points which are interior to this set, like these points, because here we have some points both the sides. Now you can of course define derivative on the boundary points by shooting them to be the left-hand derivative or the right-hand derivative. You can do that. Many books follow that convention, but that is not the right thing to do given the definition of derivative. Anyway, so coming back to the problem, f is a function from whatever this particular way of defining functions for any problem in MPT. Then what we say is, and also it's given that there exists a x naught in A to B such that this is 0. Okay. then prove that there exists some so I don't think this will so there exists some t in AB for which f prime t is equal to f of t minus f of a by b minus.
We can take the function g of x equals fx minus fa by b minus a.
Yeah.
So,
but I will wait for the others to think also for some time.
sure.
Yeah, that's right. That's right. So, Ritu, are you giving ISI this year? Are you in class 12 now or 11?
What did you say?
Are you in class 12 or you are in class 11?
12.
I am not reading the chat, okay, so because I'm only using the iPad. So if there's anything, just unmute yourself. Yeah, so any progress or anything? So yeah, who solved it? You can just say the solution now. Hello? Am I audible? Hello?
Yes, you're audible.
Okay, so whoever was saying the solution.
Yeah, I was saying to consider the function g of x equals fx minus fa by b minus a.
G of f, sorry, g of x equal to fx minus
fx minus fa by b minus a.
xz. So after this, what do we do?
Just a minute.
Anybody else solved it? Okay, so after this, it shouldn't be hard to solve. Just take cases on x naught and a, stuff like that. So what do we need? We need a point where g is vanishing. So how do we do that? What do we have in hand? Intermediate value theorem. Okay, I won't discuss the solution of it. You should try it. Okay, everybody should try it and
Okay,
get to some
instead,
solution.
I think I made some mistake. So I think it should be g of x equals f dash x minus fx by
Yeah,
b.
yeah.
Yeah, then we can apply IVT somewhere.
Yeah. Not fx. Yeah, f dash x. I also what I was saying. Yeah. So now you have to apply IVD. Now you have to find out some values you have to check, and then you have to use LMBD also inside. So I give a lot of time because these things you all should do now. Okay, like these are the standard kind of problems. Okay, anyway, I will go over it and let you try. So what I will do is I will just briefly go through the Riemann integration part and the syllabus. So now what is anti-derivative? the thing is, you
A
see,
thing
so
which we do derivative to get the function, original function
yeah,
of
yeah,
fx's.
yeah. But one thing I'm completely against it, that you shouldn't think of integration as antiderivative. Okay? So FTC is coming later. Fundamental theorem of calculus is there because it's a wonderful subject. But that's not the reason of doing integration. Integration didn't come to replace or like take the complete reverse process and get something ulta. Nothing like it came for a very pure reason. We wanted to understand. Okay, so if we give a unit square 1 unit area, 1 unit area, then what about this? How much area is this? Okay. What about this? How much area is this? All such questions, and how to define area, first of all. So all these things came on to, so what we basically knew was this, that if there is A and B, A unit length here and B unit length here, then the area is supposed to be A. That is something we are convinced. Now we have to deal with things which are not so straight. So what did we do? We had this wonderful thing in our hand that is called limit. So again, we define something in the terms of limit. So we can't really define area of this, but we can define it as a limit of some areas approximated by such slices. So that's all we did. So there are functions, and see, all these things can be. So suppose you want to measure the area of this. What we do is we divide it like this and take a function. This is a graph of a function. This can follow the graph of a function, and this can also follow the graph of a function, like on the reverse thing. And then we add the two. So we figured out that finding out the area inside the graph of a function is really a good point to start. So we started to find our area here. So I think you all know the definition of Riemann integral or not. I will not go into it, but that is from where it came. So we had functions from closed interval a b to r, and then we had the notion of integrating the function from the closed interval a to b. Okay. So this is sort of the limit. So you know what this is, right? There's a partition and there's a mesh of a partition going to 0, and then there's sum of the partition. Or you can also go with tags, tag partition, and then increase the number of tags, and then again take the sum over the tags, something on that line. Okay. So this is all about integration. Now what happened is we got a very interesting thing. We got that, and now what all functions are integrable? That's the first question. That is, all the continuous functions are integrable. Okay. When we say a function is integrable, when this limit exists. So as I said at the beginning of the class, I don't remember if I say it, but something I want to say is that our integral, our derivative, all these things are basically a limit of something, limit of some particular function. Okay, so, and if the limit exists, then we say the thing to be integrable or differentiable, and if the limit doesn't exist, then we say the thing is not integrable. So all continuous functions are integrable, but there are some functions which are not continuous but also integrable. So that we are not getting into. Now what happened is, the most important part is the fundamental theorem of calculus. So what does that say? What does that say? So anybody? What does the fundamental theorem of calculus say?
1 or 2?
Tell me anyone.
Okay, so FTC 1 says that if f is an integrable function,
Okay.
like on a
So we
closed
first
bounded
take
interval.
integrable function.
Yeah, on a
We take
closed
a
interval
to b to r, which is integrable.
is integrable. We define a function capital F of x. Define a function capital F of x as the integration from a to x of f of u du.
Ah,
F of u du for x greater than equal to 1 and less than equal to b.
very good.
So
Yeah. So f
then,
is also defined from a to b.
yeah, right. Then we can say that f is continuous then FTC says that f is continuous everywhere from a to b, and f is differentiable at those points where I mean capital F is differentiable at those points where small f is continuous, and at those points the derivative of capital F is equal to the value of that point of small f.
Can we say it pointwise? I am confused here. I know that if we include another condition on small f, that small f is continuous, then we can say that capital F is differentiable. But can we say like this pointwise?
Yeah, I think so. We are I mean FTC says that if small f is continuous at x equals x0, then capital F is differentiable at x equals x0 with capital F dash of x0 equals small f x x0.
Okay, fine. Yeah. But okay, so I don't really, I'm not completely sure about that. I need to go through the proof to understand again that if pointwise is also true. So to play on the safe side, the theorem I know I will state here. That also might be true, I don't know. That if additionally we are given that f is continuous, then what happens is then f is differentiable. We can say that f is differentiable. And then the derivative of f at a point x is f of x. So this is a miracle. This is a wonderful thing. And this is a theorem which is, how do you say, which was not expected while defining the integral. This is something which is the building block of the main, like, why do we have such wonderful properties? We have because of the fundamental theorem of calculus. This is not obvious, but this is the stepping stone. There is a discrete version about it, like version on it. You can think that. So what is basically integral? Integral is basically sum. Now you are taking many sums, like we normally take finite or countable sums, and here we are taking kind of a limit of sums. So that's the thing. We are continuously taking sums. So anyway, so that comes from this thing that, and what is derivative? Derivative is just kind of difference. So when you have, so this is, okay, so leave, I won't just go into all that. So what I'm trying to say is that when you have kind of differences and then you sum them, it gives you back the one small thing you started with, right? That sort of intuition. I have to speak a lot to go deep into it, but okay. So this is FTC 1. This is FTC 1. So here we are starting with the integrable function. And then we are taking the integral of the integrable function to a point and getting it to be a new function, capital F. Then we are saying the capital is continuous. So this is not a very important part. What is the important part? If we start with a continuous function and then integrate it up to a certain point and call it another function, which is kind of the summation function, this kind of integral function. Then that integral function is differentiable, and the derivative of the integral function is a function itself. So this kind of says that derivative of integral is okay. Now, what does FTC2 say?
Should I say?
Yeah, yeah.
FTC2 says that if f is a function that is, if f from closed interval a comma b to r is
Yeah.
differentiable and its derivative is integrable, then
Yeah.
the integral from a to b of f dash x dx is equal to fb minus b.
Exactly. Exactly. So we have to start with a differentiable function, right? Now what we do is we integrate the derivative, and this gives us fb minus f. This is a simpler version. So I will just state the discrete side of it. So suppose you take fx I minus fx I minus 1 and sum them. What do you get? Get fx n minus. This is what is happening in a continuous pattern. This is the idea of fundamental theorem. I am not sure if you are getting this small part I have written here, but this is all about. This is the thing. So these are the two most important theorems of calculus. Now, unfortunately, I don't really have much time. So there is one important. So now what you have to do is to get all the important theorems of. See, ISI will never ask you about hardcore integration questions because for that you need Riemann integration, Lebesgue integration, and then after some major theory and concepts like that. The big theorems on Riemann integration are given by the measures of the set of discontinuities and stuff when a function is Riemann integrable and things. So what they will basically give you is the differentiable properties you have studied so far in a integral look of it. So what does FTC allows you to do? It allows you to go from integration to differentiation and so on. And again come back. So you don't want to come back from derivative to integral, right? Because derivative is something uncomfortable. You know so many theorems on it. You can find derivatives so easily. So what we really do is we take problems say, of integral and then somehow transform it to a problem of differentiation and then we solve. So basically there are theorems like MBT and IBT on integrals as well. And they're just the analogs of them in the differential part. So I had one or two problems to discuss today on integral. So let me just give this one. But sure. So I don't think we can. So there is basically, and okay, so the theorem I want to state is like this. It says that integral a to b of f is equal to f of c times b minus a for some c. So you can try to prove this. That is something. And then if a two integral functions, and something like this also will hold a by vf. Sorry, it will be of g. Let's see by bc. Some sort of things like this. Okay. So all these are again going back to the mean value theorems and stuff like that. Yeah, so try to figure out why are they correct or whatever.
We can write the integration of f from a to b as psi b minus psi a, where psi dash x equal to fx.
Yeah, exactly.
So if for taking the left side, integration of f from a to b is equal to we are just taking psi b minus psi a equal to psi dash c into b minus a
Yeah.
by the mean value theorem.
Exactly.
And then
So
we
you're
are
just applying the mean value
substituting the value of integration
Yeah.
of a to b. If
Exactly. So that is the
and
thing,
then
as I
c is fc.
yeah. So as I said, whenever you are looking at a problem of ISI or whatever of integration, just try to somehow convert it to the derivative side of it, because you are comfortable with the mean value theorem, say derivatives here and stuff. So that's all about it. Okay. And there are a few individual problems which are special to the theory of integration, but yeah, so they are somewhat like those problems are mostly again on the maximal value theorem, that the maximum value in the continuous function. So those formulas will be given on a continuous function. Then you have to use something of a continuity inside the integration. So that's not really about the integration. That's about some inequality or stuff like that. There is a CS inequality which holds for integration. That's also interesting and important too. That is this: if g is less than equal. So all these things you have to keep in mind. You can just look at the results of people, and that's all about it. Okay. Okay. So if there's any doubt, let me know. Otherwise, I think.
Sir, could you go back to some 5-6 pages later? I could not catch
Yeah,
that.
definitely. Definitely. Which one? Which page? This one?
I think no, the later one.
This one?
Yes, sir. Yes, sir. This question: f of t minus f of a.
Yeah. So this is the homework. Like after this is just
Oh, this is a
the
homework.
same. Okay. So just figure out this. We want some point where this thing is zero, and we have this particular fact. Try to use it.
Yes, sir. Sir, and going back to the first question, sir, where you said something about linear something. I could not
Yeah.
follow up that.
Okay. So just just quickly telling what I'm trying to say is, whenever you are taking derivatives at a point, that's a tangent. What most people say. I don't like the word tangent, but okay. So there's a tangent through it, right? Kind of. So when
Yes,
you extend the straight line, we say this to be a linear approximation of the function. So if this is the function, there's a line, there's a straight line. We approximate the function by the straight line around the point 0. So around 0 or around the point where we take the approximation is quite good. By quite good, what I mean that this is something you need to write.
got
This
it.
is the whole thing. Everything is in this place.
So that error part, what is the intuition behind like solving problems like you did in a function question?
Yeah, actually the thing is, you see, the real analysis is something which is also like you were studying as calculus in 10+2, then people are studying in their undergraduate courses, and even some of the college universities are getting them in their graduate courses. So
Sure.
see, the thing is, maybe I shouldn't give all these ideas to you right now. This might not be completely like suitable for you, but what I'm trying to say is maybe you look at the problem the way the guy who solved. So like if F0, the thing is we want to get from the outer points, the points that are far away from 0. From those points we want to get to the points closer to 0, because around 0 we know how the function is approximate. Because we know the derivative at the point 0. So we know how the tangent is to the function at the point 0. So we know how the function is around the point 0. And we have an equation from where we are taking all those far away points and going back to the points close to
Got it.
0. Do I make sense? Do you now understand what I'm trying to say?
Yes, sir. Just a little bit of looking again, and I'll be good to go. Thank you, sir.
Okay, great. So definitely, yeah, you understood the solution, right? So the solution is pretty clear. But what I'm trying to say is all these solutions are coming from a unified idea, and holding such ideas often help in exam, because there you will not get any, most probably will not get any common problem. You won't know the particular technique to solve it, but those unified ideas can help you to, okay, so I don't know the exact technique, but I know the idea, so I can develop a technical. So that is the thing I keep in mind while posing some problem or giving out the solution. I hope it helps.
Sir, can you send like a sheet of problems that you can do and solve?
See, the thing is, problems are finite, and so many mock papers we have to make, and then these model things and all. I didn't know that 5 mock tests you guys are going to give. Like all these decisions are not. So the thing is, problems are quite limited, man. From where will you get this infinite source of problems? Now we have to just go and like copy paste problem from the internet sources, and that is like no use of doing it. So yeah, just solve books. What else can I say? All the problem sources I had. So the thing is, I had a notebook which is not with me right now. That's in Bangalore. So I don't really have access to that. That was a notebook I used to do when I was like the notebook I used to make when I was in 10+2. But except that, the books I knew, the books I followed, which were a little bit rare, all the problems are going out. Okay, so the problems you're doing in class, problems in mock papers. So I don't really have many more new problems. Still, I will try to give you a list of problems if I can. And I think there are model papers and many materials are given to you. These mock tests are there, so enough of practice is there. The thing is, you don't really need to solve 100 problems. You really need to understand the solution of one important problem. That is something I would suggest. Because by solving one problem to its fullest, you can be ready to solve 5 more problems like that. But solving 100 problems and just knowing specific solutions to them, won't help you to solve the 101 problem. Okay,
Sir,
so
the
yeah,
last question, sir, is it
yeah,
it's out of context, but I'm
yeah,
just
yeah,
curious.
definitely.
So if we draw something in something randomly in graph, can we find its function? I mean,
Okay, so something randomly as a graph,
yeah.
like you were saying, like we need to maintain some things. Like you can't draw a graph like this. This is not a graph because this doesn't follow the vertical line test. Do you know this? Like, do
Uh,
you understand why this cannot be a graph or function?
no, sir.
Because see, if this point is x, then this is also f
Oh,
of
got
x,
it.
this is also f of x, but the function is not well defined. So this is called a vertical line test. So a function cannot pass through the same vertical line more than once, the graph of a function. So that you have to, this thing, you have to maintain, this constraint you have to follow. Except that, yeah, pretty much, you can draw any function like that and just give the value of that point to that function. You may not draw a graph also. Like there can be functions which you can't draw, you can't really draw a graph. So suppose fx equal to 1 at all the rationals and 0 at irrationals. So this is a function, right? But how do you really draw a graph? The rationals and irrationals are so densely packed. You can't really, like the human eye can't like, you know, you can't really draw a function. You can't really draw a graph of this. But yeah, pretty much. If you draw a graph, you can extract a function from it if that satisfies few basic things like this vertical line test. Yeah. Okay. So any more doubts you can. So I don't know if I will take any more class. I may take one or two. That depends on how many geometry classes we will have and many other stuff. So I'm not deciding really on that. So if I get another class, then maybe I will discuss one or two important problems on integral calculus and then start whatever the new topics assigned to be. Okay. Is there anything else? Anything you want to discuss about? Any comments? Any feedbacks? Otherwise, you can call it a day. Okay then. All the best for the exams, and all the best for any kind of mathematical journey you take.
Dada,
Yeah.
you have graded one mock. There were certain questions which majority of us couldn't solve. Can you please give solutions to those?
Which one? I discussed the solution of mock 1, a mock 2, right? In the previous class. Is there any problem from mock 2 which you guys are not getting solution to?
No, I'm talking about the other mocks.
The other mocks I haven't graded. Like I didn't set the question paper. So okay, mock 3 I guess the question paper was mine. Yeah, so mock 3 was I set that purposefully a little bit difficult. So yes, I will send solutions of those questions if you don't get. I don't expect everyone to get all the questions of mock 3. I don't really know if that is mock 3 or mock 4, but yeah, so there was a question on the question which had this ambiguity, this f and mod f thing. I think that is mock 3. So yeah, so those solutions I will discuss. Okay, don't worry about that. Somebody will grade the copies and then somebody will give you marks. I don't
Sir,
really know all of that.
sir,
When
what
will
mock
that be?
test workshop? Sir, what mock test is it the workshop?
Is it the workshop? I don't. There are 5. Apparently, they will take 5 mock tests. Okay, and see, so many mock tests you are giving. Like I at least never give 5 mock tests in a streak like this. I don't know. It might help. It might not help. Like try to be sure that yeah. So these questions, all the questions you are solving, you are giving time to the questions, half an hour or 10 minutes or whatever. You should try to figure out the solution and then try to get some extract something from the problem. When you're wasting your time or giving your time on a problem, let that be mock test or a problem you are just practicing before exam. It's not enough to get the answer to it. You have to get gain something from solving the problem, right? That's why we solve problems. That okay, so I understood this part more more in a more unified way. So something like that. So yeah, so let me know in the group, in the fractions ISI CMI group, or wherever you can, or you can DM me too, that which are and all specific problems you are stuck at. I don't know when the copies will be graded, but I'm waiting for them to be graded. Maybe I will have to grade them. So I will do that in a while when I will get time.
Did you give
Don't
any
worry about that.
mock 4?
Yeah. Sorry?
Did you give any question in mock 4?
No. I only gave 2 set of papers, and I don't know. I saw the mock 2. That was my paper. Like not entirely, but yeah, there were questions of mine. But there must be another paper that is, I guess, the mock 3 itself, which I give the paper. So I actually gave the questions. Mock 4, I don't think the questions were not mine. So most probably I will not grade any of them, but I will see. Okay, so don't worry about that. Before the workshop ends, you guys will get to know your scores. And I guess there is a plan to take the average scores and do something, I don't know. But yeah, so you will get to know your scores. You will get to know the answers of the problems. I guess many of the problems were already there in the model papers they gave you. Okay, so don't worry about that very much. What I'm saying is, don't worry about the marks you get in the mock test, or don't even worry about the mock test too much. Worry about the things you are learning and your final grooming for the exam. Okay, so yeah, I just DM me with whatever problem you are having in mock test 3. I will try to give you a solution of that, or check your copy to give you some feedback of how you have written the problem or what should be improved or what. Okay, so generally what I saw from mock test, grading mock test 2, the writing skill is fine. This is something which is rare from whatever experience I had before teaching. People really mess up in their writing. But this is something I saw here, that most of the people who wrote solutions to a problem wrote it quite fine. So that's a very good point. That's a really very good point. If you know how to write a problem, then you won't get a like, now it's all about you to solve problems. Okay. So that's really a good thing. And the bad thing which I saw is, in some cases, choice of problems. This is also an art. You have to look at the paper. You will not solve 8 of them, but you have to quickly get to the problems you think you can solve those, right? So you shouldn't waste your time on the hardest problem on the paper. So that is something you need to check on a bit. And then I think someone of you misread like 2 or 3 questions. So take care of that. And another one, that I intentionally gave 2 or 3 questions in the mock 2 because I was able to set an easy paper. So I just tried to give easy questions, but in a different, outlook to it. So that is something you should think of. Okay, whenever you find there is kind of ambiguity in a question, like A, B are not given to be distinct, but they're in most cases given to be distinct, but understood to be distinct. So don't assume what they're trying to say. Go for what is exactly written in the question paper and answer to that. Even if that was a printing mistake, they are bound to give you a number. Okay. So don't really assume that this guy is trying to say this, but okay, he forgot to write A not equal to B. So I will write assuming A not equal to B. And here you are writing explanation to a particular answer, and then I'm checking it, I'm understanding, okay, you have understood the problem, but you have given the wrong answer. But that is not the case in the ISI calculus, right? You need to give a particular response to your own one. And at that time, if there is a confusion regarding it, don't assume anything about someone who is setting the question paper. Just assume what is written on the question and answer to that. And even if that is wrong, or even if there is a silly mistake in the question paper, they're bound to give you the answer. They're bound to give you the number. Okay? So that is something also I wanted to say on the feedback thing of the paper. Nothing else. Okay, you just solve few problems, understand good mathematics, try to enjoy mathematics, and yeah, that's it. Okay, is there any other questions or anything else? If not, then this will be it. Good night. Okay. All the best for the exams. I'm an intern.